Thank you. Thank you very much, Elizabeth, for the introduction as well. So good morning to all, and sincere apologies for not being able to be there with you in person today. But I'm very glad to deliver a few words and a few messages for you, notably on the EU position on these issues, which are very important to us. Also to illustrate a bit the contribution of the de facto project to these priorities, and to talk a bit about the challenges and future developments in this regard. So if we can move on to the first slide, please. So I don't see the screen moving. I don't know if it works on your side, but maybe I will start and we'll see later. So indeed, for us at the European Union, the modeling and the digitalization of battery testing are important tools that on one hand would help us speed up the design and the manufacturing of batteries by optimizing production processes, keeping batteries in function for longer, and on the other side to reduce the reliance on costly and on time-consuming trial and error methods, so therefore improve the design of the batteries as well. And in that sense, they are important future-oriented activities. Yeah?
Yeah, the thing is that we cannot hear you properly. I don't know if it's a difficulty with the wireless connection or yeah.
Sorry for that. I will try to be slower, then maybe it helps. So in that sense, for us, these topics of the digitalization of battery testing and manufacturing are indeed important future-oriented activities, which are fully in line with two of the most important Commission priorities for this year, so which are digitalization and the greening of the economy, what we call the Green Deal. To illustrate this, I'm sure you are all very much familiar with the co-programmed Horizon Europe partnership that the EU has built with research and innovation stakeholders in the battery domain, which is called BAT4EU, for which actually digitalization features as a cross-cutting priority of interest for both us, the EU, and industry, along safety and security issues as well. If we can move on with the slide. So, as I mentioned at the beginning, yes.
Okay, Alessandro, maybe it's. Would you mind closing the camera? Maybe it will be better, the connection. Yeah. We will try to fix it because it's like intermediate.
Sure, no problem. I hope it's better now.
So yeah, maybe I should be shifting to the next slide.
Yes, please. Yeah. Great, thank you. So as I mentioned, for us, the digitalization is important for two aspects. So on one side, the artificial intelligence in the battery sector has supported the discovery of new materials and the optimization of designs in a way that is much faster and much more accurately than traditional methods. More research data could therefore be processed with less errors and with increased focus. Simulations of material properties and performance have also helped fine-tune the design of batteries before physical experiments, therefore greatly accelerating the discovery process of materials and saving resources. On the other side, as I mentioned, the digital models have also proved useful in the design and outline of a production line, controlling and operating the line and optimizing its operation. Digitalization also facilitates the integration of various aspects of the battery manufacturing process, enabling seamless communication between different stages and optimizing overall productivity. But what we figured out, and also the project have pointed out, is that by digitalizing cell design and manufacturing process, also the sustainability, the optimization, and the flexibility solutions are supported as well. Digitalization improves also the understanding of battery performance, notably under sustained fast and super fast charge cycles, informing the end users on optimal usage profiles for minimum capacity and performance degradation, and supporting manufacturers to closely manage the performance of battery cells. In recent years, there were, from our side, a number of call for proposals on these topics, which illustrate our continuous support to these issues. Just to give a few examples, so last year in 2022, there was another call on digitalization of battery testing from cell to system level, including lifetime assessment, under which 3 projects were financed and have received implementation. And basically, they will contribute to most of the impact expected also from de facto projects, so to improve the competitiveness of the European battery industry across the value chain, to shorten the time to market, to reduce the time and cost of battery development by at least 20 to 30%, to improve battery design in terms of lifetime, reliability and safety, and reduce investment and operational costs. While this year there was also a topic for which evaluation is still ongoing, but which is aiming at creating a digital passport for tracking battery materials, optimizing battery performance and life, validating recycling, and promoting a new business model based also on data sharing. If we move on to the contribution, to the concrete contribution of the DEFACTO project to these priorities. So DEFACTO is indeed deploying digital open source solutions to boost the development of next generation lithium-ion batteries for the automotive market, as you all know. It particularly contributes to the development of integrated software tools that describe behavior with maximum accuracy and at reasonable computing costs, optimizing the design of a cell by including all relevant design variables and analyzing different physical domains. It also helps reduce the number of experiments needed in the cell development phase, contributing to the standardization of measurement procedures, and helps us create new market opportunities and improve industry competitiveness. There were a number of significant effects to which the DEFACTO project contributes, notably the reduction of the development time and cost for battery cell up to 30% each, to developing a better optimum of the design and to the analysis based on different physical domains, to demonstrate the potential for the reduction of the number of experiments by factor 3 for the overall development process, and to reduce research and innovation costs for batteries by 20% overall. Concretely, what the project has achieved, it's a number of things, starting from the manufacturing of more than 130 cells. The project has also conducted detailed multi-scale post-mortem analysis from macro level, so the visual inspection, to nanoscale, and from bulk to surface. 12 modeling tools have also been developed covering the electrode fabrication steps, electrolyte filling, as well as cell aging. One advanced optimization tool has also been developed. 2 chemistry cells have been used for models validation. Electrolyte cell guidance, enhancing energy density has been suggested based on the optimization algorithm described previously, and 2 Senelec workshop agreements have been proposed as well. And last but not least, 13 publications were accepted, 3 are under review, elaboration, and 3 more are planned. So of course, it's very much important to come up with research results, but it's very much important as well to make them known to the public as well. Moving on to the next slide. Despite all this progress, of course, a number of challenges still persist, notably related to the availability of high-quality data that can be shared and that can be exchanged globally in line also with FAIR principles, as well as the development of digital skills and knowledge among researchers. We've also noticed that the design of relevant and accurate models is still very much resource intensive nowadays. However, we think that a lot of progress was achieved in recent years in standardizing digital tools and sharing infrastructure, as DEFACTO and also later on Modelli Square will show you. This, of course, has improved and will improve in the future our battery research capabilities and will support the building of a common knowledge base for the battery industry. These 2 projects and the others that I mentioned have also shown how crucial it is basically to test and to conduct simulations with different materials, with electrode design, cell formats, and cell chemistries. To end up, probably talking about the future research. So in our view, future research on digital twins is particularly needed to link complex issues such as the performance of batteries with material properties, but also with cell design, manufacturing processes, as well as sustainability issues, and also to make these things, these tools on one hand increasingly sophisticated, and on the other hand accessible to the big numbers and also to the industry and to the gigafactories. So I will maybe stop here for the moment. Thank you very much, and I'm very much looking forward to hearing from you throughout the day of the progress so far and what remains to be done next.